good morning to everyone, and welcome to a course on renewable energy systems, which I will give you. If you don't know who I am, I'm from the University of Calgary in Canada, and I'll tell you a little bit about myself in the next slide. I put up on the title page my email address, or two email addresses actually. So if you have any questions or queries, or you want further information about what we're talking about today, please feel free to contact me. So I'm going to spend 2 days a week for the next 7 weeks. I think that's how we've organised it, to tell you about renewable energy systems. But before I start that, I thought I would tell you a little bit about myself, because it's important in a couple of ways. One of those ways is that I was born in Australia. I was actually born in Sydney, which is probably the city in Australia that's most known around the world. And then for many years, I lived in Newcastle, which is just north of the city of Sydney. And you've probably already noticed that I speak English a little bit differently to a lot of other people speak English, because Australians have a very distinctive way of speaking English. I think that might make it more difficult for you people listening to me, because not only do you have to listen to a lecture in English, but you have to listen to a lecture in English spoken by a person whose accent you probably are not familiar with. I've talked to Rustam about this. If you do have problems understanding me or want me to repeat anything, please either put your hand up or send me a message in the chat, and we can revisit the material. Okay, so that's the first thing about me that you need to know, that I'm from Australia. The second thing you need to know is that I'm a mechanical engineer. I studied mechanical engineering at the University of Sydney and did a master's degree in mechanical engineering. And that's going to become important when we get on to talking about photovoltaics, because when we talk about photovoltaics and about the basic processes by which photovoltaic energy is produced, you probably know a lot more about it than I do, because you guys are physicists. So I'm apologising right at the beginning if I don't give you good explanations for what happens then. So I started out as a mechanical engineer, and then I went to Imperial College in London to study aerodynamics. Imperial College is a very famous university in London and has a very strong aeronautics department. I did my PhD there in aerodynamics. And when I got back to Australia after doing my PhD, I taught at the University of Newcastle. That's a town north of Sydney. And I taught there for quite a long time before leaving in 2004. And I worked in the wind industry because when I got back to Australia from Imperial College, I started working in wind turbine aerodynamics. How do you design wind turbine blades to get the most power out of them? Or how do you do multi-dimensional wind turbine blade design? What are the basic theories that we use to study wind turbine behaviour? So I did that for quite a long time. Then I worked in the wind industry for about 6 years, mainly in my own business. We were developing wind turbines ourselves. And then in 2010, I took my present position at the University of Calgary. They invited me to apply for a professorship in renewable energy, and it was a wonderful opportunity. So I moved from just north of Sydney in Australia to Calgary, which is in Alberta. This is the province that I've highlighted with my laser pointer down here. It's the second province in from British Columbia next to the Pacific Ocean. And Calgary is right down at the bottom there. And the border between British Columbia and Alberta is actually the Rocky Mountains. And the southern part of Alberta gets very strong winds from the Rocky Mountains and is a great place to generate wind power. And when I came here in 2010, I got involved with quite a bit of wind energy research related to the particular conditions that we have in Alberta. I'm also involved in a number of academic journals for energy matters. I'm editor for Wind Energy for Frontiers in Energy Research, which is a well-established European journal. I also am an associate editor for Energy Sustainable Development, which concentrates on energy issues for developing countries. And that's one of my big motivations for doing this work. I work with people in Ethiopia. I work with people in Uganda, Egypt and Morocco in wind power and other projects. I'm also a director of the Wind Energy Institute of Canada. And the Wind Energy Institute of Canada has a wind farm right over on the eastern side of Canada on a place called Prince Edward Island. And as a director of that Wind Energy Institute, I get to learn a lot about how the wind farm that the Institute owns, it has 5 wind turbines on Prince Edward Island. I get to learn about a lot of the operational issues, the things that are causing problems with the turbine operations and how they get fixed. So that gives me a reasonable amount of practical experience in how you actually generate electricity from wind. My current research interests, I work in wind and solar forecasting. How do you predict how much wind power you're going to get in the future or solar energy? Most of my work is actually in the area of wind turbine aerodynamics. I'm still following on from my PhD work many years ago. I have a particular interest in small wind turbines, in their design and operation. And over the last 7 or 8 years, I've also got involved with small hydrokinetic turbines. Unfortunately, I'm not going to get much opportunity to tell you about my current research interest in these lectures, but I would be very happy to discuss anything that people have either offline after the lecture or by email. Okay, one of the reasons that we're interested in renewable energy is the issue of climate change. And the publication from the International Panel on Climate Change that came out in 2021 is showing very clearly the way in which the Earth's temperature is increasing due largely to human activities in terms of emitting greenhouse gases, of which carbon dioxide and methane are the most important. I'm going to say very little about specific climate change issues in these lectures. I'm going to assume that they form the background of why we're interested in renewable energy and why we're pursuing renewable energy. But one of the important points that I want you to get out of these lectures is that renewable energy can stand up for itself independently of climate change issues. I hope I will convince you over the course of these lectures that, generally speaking, renewable means are the cheapest ways of producing electricity in the early part of the 21st century. So even though the climate change mitigation is extremely important, I think there are other reasons why we are interested in renewable energy. Okay. We're going to have the lectures on Wednesday morning and Thursday morning your time for 7 weeks. This is the way in which I propose to give the lecture material. So the first 2 lectures will be an introduction. I intend to go through the material in this PowerPoint in those 2 lectures. So what I've called a lecture in terms of the time that we are actually meeting, that doesn't necessarily correspond to a lecture in terms of the PowerPoint presentation that I'm going to give. So I expect, for example, that this PowerPoint presentation will take today's lecture and tomorrow's lecture as well. So that will provide the introduction. And then we move on to hydropower, the first of the electricity generating technologies that fall under the heading of renewable energy. We're going to have about 3 lectures on hydropower, about the same number of lectures on wind energy and solar photovoltaics, and then we will finish up talking about energy storage and system integration. How do we cope with at least 2 of these technologies, wind energy and solar photovoltaics, that are inherently intermittent? They produce electricity when the sun is shining or the wind is blowing, not necessarily when you or I want to turn on the lights as we go into a room. How do we deal with that? Energy storage is one of the ways that we deal with that, and system integration is another way. We're going to concentrate on technologies for electricity production. So we're going to look at wind energy and solar photovoltaics primarily for electricity production, rather than things like hydrogen production, which is becoming an important new area for both wind and solar. And we're also not going to talk about solar thermal systems, where we use solar energy to generate heat, which can drive turbines or do other things like that. Even cutting down the number of technologies that we look at to 3, hydropower, wind energy, and solar photovoltaics, there's still not very much time to look at the fundamentals of those energy technologies. So we're going to look at how hydro turbines, wind turbines, and photovoltaic modules work only at a very superficial level, only to the extent that we can understand how they operate when they are given the energy resource that they get when the wind blows over a wind turbine or the sun shines on a photovoltaic cell. I'm also not going to say very much or anything more in this lecture on hydropower. This lecture is a general introductory lecture, so we need to have some idea of the global context of these technologies. And a very good place to get that information for hydropower is the 2021 Hydropower Status Report that is put out by the International Hydropower Association. I downloaded this report myself and I put it up in Google Docs so you can look at it directly there. Probably a good idea to do it when we start looking at hydropower next week. Okay, so this introduction is going to concentrate on wind and solar photovoltaics. And one of the best places to get detailed information on what's happening with these technologies is from the US Department of Energy, particularly their National Renewable Energy Laboratories, which are mainly headquartered in Colorado, which is fairly close to Alberta. Every year, the Department of Energy puts out a market report on wind, both for land-based and starting in 2021 for offshore wind, because offshore wind energy is becoming an important part, or is starting to become an important part of the US electricity market. So on the left, you can see a typical wind farm, probably in the Midwest of the US, because that's the windiest part of it. And you can see a number of modern large wind turbines. Modern large wind turbines typically have 3 blades, and typically the blades are upwind of the tower. In other words, a vertical tower that is holding the nacelle for the turbine, which contains a generator and some of the power electronics. The blades are ahead of the tower, so the wind would be coming from me towards that wind turbine. It's a very interesting question how the technology has matured to form this typical or standard idea or standard exposition of a wind turbine. Virtually all large wind turbines are three-bladed, and the blades are ahead of the tower as far as the wind is concerned. And you might like to think about what are the reasons that this layout of the wind turbine has come to be common. And you can see when you go to the offshore wind area as well, it's pretty much the same thing. You can see three blades on a large tower, and the blades, excuse me, are ahead of the wind. Okay, the US market reports on wind energy have some really interesting information in them. What you see here is a year-by-year account of the technologies that have been installed in the US as additional electricity generators. So in 2011, 29% of the new electricity generation plants was wind, and the others, a little bit of solar in 2011, quite a bit of gas, more gas than there is wind. And if you look at the trend from 2011 to 2020, you'll see that wind has gone up somewhat, but solar has made a big increase in the installed generation capacity. And particularly, I'd like you to note that coal and other non-renewable technologies have just about left the scene. It's been a long time now since a new coal-fired power station was built in the US. And if you look at the data going back from 2011, I've seen the data for all of the 21st century. This trend is typical of what's happened this century. The overwhelming proportion of new generation capacity in the US has been wind, solar, and gas. Now, gas is actually a very good technology to have with renewable energy. Does anybody know the reason why that I made that statement? Why do you think I said that gas is a good technology to have with wind and solar? Okay, if you feel like, if you don't feel like answering the question verbally, feel free to use the chat. I think I can find where the chat is. Maybe Ivan and Ruston can help me with it anyway. The reason why gas is important in the context of renewable energy is that gas-fired electricity can be turned on and turned off very quickly. Okay, I'll get onto that point a little bit later in this presentation, but you can probably already start to think about the issue of what happens if you have a large amount of renewable energy on your electricity grid. At the moment, around the world, wind and solar are producing less than about 10% of the electricity around the world. But if we're going to mitigate the problems of climate change, that percentage has to increase dramatically. And if that is the case, the problems with intermittency may also rise dramatically. And so if we install, along with the wind and the solar, other technologies that are comparable or I'm trying to think of the right word, that fit in with wind and solar like gas does, then that's a good thing to do. Okay, here's some facts about wind turbines that have been installed in the US. So what we see here over a 20-year period is the average rated power of the wind turbine, sometimes called the nameplate capacity. And the nameplate capacity or rated power is always the maximum power that a turbine can produce. So if I buy a 2 megawatt wind turbine, then that means that that wind turbine will produce a maximum of 2 megawatts. The same thing occurs for photovoltaics. If I buy a 300 watt photovoltaic module, then that's the maximum amount of power that can produce. So nameplate capacity is the grey bars, and you can see the scale on the left. So in 2020, the average rated power of wind turbines installed in the US was somewhere between 2.5 and 3 megawatts. What that means in terms of the hub height, the height of the axis of rotation of the blades, typically about 90 metres, with a rotor diameter somewhere over 120 metres. Okay, so the big changes that have happened over that 20-year period has been an increase in the rated power from less than 1 megawatt to somewhere less than 3 megawatts, and a significant increase in the rotor diameter. In other words, typically wind turbine blades are getting larger. And I'd like you to think about what might be the reasons for that trend. Why do you think the blades are getting larger, but the hub height is not changing all that much? I'll come back to that point later on. Okay, this slide shows you probably the most important single number that relates to renewable energy generation and renewable energy projects. It's called the capacity factor. It's a factor, but it's usually given as a percentage. And the capacity factor is the average power that you get from a wind turbine or a photovoltaic system divided by the maximum possible power. So typically in the US, we're sitting at around about 40% capacity factor. So that means that if I have a 2 megawatt wind farm, on average, it's producing 800 kilowatts of power. Okay. And if you think about it, the capacity factor is extremely important because it basically tells you how much electricity you're going to produce at a site, and therefore what is the income you're going to get from your wind farm or your solar farm. So in deciding whether to go ahead with a wind farm project or a solar photovoltaic project, one of the most important things that you need to do is to estimate what the capacity factor for that site is going to be for the period of your project. So typically 20 years for a wind farm lifetime or 20 years for a solar farm lifetime. And a lot of what we're going to do in this course is look at how capacity factors are calculated. Because what's interesting about the capacity factor from the technical perspective is that it's a combination of the way in which the technology performs with the specific conditions at the site. So it actually combines the productivity of the generator with the conditions at the site. And as I said, we're going to spend a lot of time looking at how capacity factors are calculated, particularly for wind power and for solar power, although it also comes into hydropower projects as well. Okay, so I said at the beginning that our interest in renewable energy stems a lot from the issues of greenhouse gas mitigation, but I want to spend a little bit of time talking about the cost of renewable energy, because generally speaking around the world, renewable energy has become the cheapest way of generating electricity. So, for example, this information, again, this is taken from the US Wind Market Report, shows turbine purchase price versus year. And you can see that from somewhere around 2008 to the present day, there's been a drop in the price of over a factor of 2. That's a huge drop in price. And if you look at the corresponding figures for photovoltaics, they're even more dramatic. If we look at the installed project, I need to go back one slide because I wanted to just point out that it's an easy number to remember. the cost of a wind turbine is about $1,000 per kilowatt. So a 1 megawatt wind turbine will cost about $1 million. When you install a wind farm project and you make the electricity connections to the grid or all those other infrastructure things that you have to do, that increases the cost by, roughly speaking, a factor of 2. So if a turbine costs about $1,000 per kilowatt, a wind farm will cost about $2,000 per kilowatt. But again, you can see how that average price is dropping significantly. And here's just that information put in a slightly different way. I'm not sure exactly why I put those two figures on the same graph. Okay, that reduction in the cost of wind turbines is reflected in the price that the wind farm owner is getting for their electricity. One of the important acronyms or abbreviations that is used in renewable energy is a power purchase agreement. This is often an extremely important part of the way a wind farm project or a solar farm project is developed. If I am developing a wind farm, I'm making an investment for somewhere around about 20 years. That the average lifetime of a wind turbine with proper maintenance, some of those issues we'll come on to later in this lecture, is around about 20 years. So if I'm going to invest $2 million per turbine and maybe 100 turbines in my wind farm, I need to have a pretty good idea of how much I'm going to be paid for the electricity that I produce. And most of the wind farm projects that have been developed in the Western world, for sure, I'm not so sure about Russia, that development has been done in the context of a power purchase agreement. So if my wind farm is supplying electricity to the Alberta electricity grid, I will try and make an arrangement with the grid operator to sell the operator my electricity at a fixed price. And that price, as you can see here, in terms of US dollars per megawatt hour, has been falling substantially over the past decade, from somewhere around about 80 US dollars per megawatt hour down to somewhere around 20 US dollars per megawatt hour. So that's extremely cheap electricity. That in terms of the retail price of electricity in Western Europe, that is about 10%, 1/10 of the retail price of electricity in Western Europe. So you can see that wind power has become extremely cheap. If we go to offshore wind, then the same trend of decreasing price has occurred, but the actual magnitude of the cost of offshore wind is still substantially greater than the price of onshore wind. Typically, it's at least twice as expensive as onshore. So the question is, why is there so much offshore wind power? Why do you think, particularly in Europe, countries like Germany, the Netherlands, England, or Britain and Ireland are establishing large numbers of offshore wind farms? Anyone like to make a guess, or anybody have any further information on that? Okay, so a chat has come. Yes, someone has suggested noise is an issue. That's a very good point. That's part of the answer. And if you add on to potential problems with noise, if most of the places that you travel in Europe, it's very hard not to see a wind turbine. So much of the onshore area in Europe has been taken by wind turbines that they're actually running out of space. So going offshore is one of the ways of getting around that. If you combine that with the fact that wind turbines produce noise that some people don't like, they also have an effect on the landscape, a visual effect on the landscape that other people don't like. One of the reasons to go offshore is that you get away from a lot of those problems. So the issues of noise, the issues of whether you like looking at wind turbines or not, those issues become less important if you go offshore. And the interesting thing about offshore wind turbines is that when you build a wind project offshore, the cost of installation of the turbines rises dramatically. It costs a lot more to install a turbine in the water than it does on land. So what that means is that the people who are building offshore wind farms, they want to buy the biggest possible wind turbine that they can get. And I showed you before that the average size of onshore wind turbines in the US is around about 3 megawatts at the moment. The largest turbine that you can buy for offshore wind power at the moment is 8 megawatts, about 3 times bigger than the average size of the onshore turbines. The bigger turbines are more expensive in terms of dollars per kilowatt or megawatt produced, but their installation costs go down when you put them in the water. So the big driver for the increase in wind turbine size, and this is an issue that we will look at when we get on to the section on wind energy, has been the offshore wind market, where they want bigger and bigger, always bigger and bigger wind turbines. And I put this information on the bottom left here. I forgot to give the reference for that information. I apologize for that. But what it points out is that Russia has some of the best offshore wind resources in the world. And it's quite interesting. It says here that Canada also has very good offshore wind resources. It doesn't say that Australia also has very large offshore wind resources. So by a matter of luck, I'm associated with 3 countries that have the overwhelming amount of offshore wind in the world. I think it will be quite some time before countries like Russia and Canada and Australia actually exploit those offshore wind resources, but I think it's very much something that you're likely to see in your lifetime. So part of the point about looking at offshore wind turbines is to understand that the big driver, the big impetus for increasing the size of wind turbines comes from the offshore wind market. Okay, so it looks like it's frozen up on me. Just wait to get to the next. Okay, so that's all I'm going to say about wind energy for this introduction. We'll come back and look at it in more detail later on. I want to move on to photovoltaics. And again, I'm taking information from the US Natural Renewable Energy Laboratory because it's a wonderful source of information about renewable energy projects generally. And their equivalent of the wind energy market report is the solar photovoltaic system, and they've now combined it with energy storage as their cost benchmark. And the latest that I could find comes from Q1, which would be January to March last year. One of the difficulties or one of the interesting things that you have when you teach a course like this is that every time you teach a course on renewable energy, you have to update your information, because you've seen from the previous slides how rapidly the price of wind turbines has decreased over the last 10 years. Same with photovoltaics, same with storage, same with lots of other components that go into renewable energy systems. So every time I teach this course, I have to update my information. So here's a typical photovoltaic system. You can see that the modules are fixed. There's no tracking of the movement of the sun in this solar farm here. Each one of those units of the solar farm is a module. That is a basic component of a photovoltaic system. Typically, that module would have a rated power of around 300 watts. So it's very easy to estimate the capacity of a solar farm just by counting the number of modules it has. We're going to be looking at the basic principles of operation of photovoltaic systems. As I said right at the beginning, that's an area where my knowledge of it is probably considerably poorer than yours, and you'll probably have to help me in this. And then we're going to be looking at issues like, is it worthwhile to track the sun? If we add mechanical complexity to this system by changing the orientation of those modules as the sun goes over the sky, both daily and seasonally, do we get more power out of the system? And is the cost of getting that more power justified? There'll be some of the questions that we're looking at. Most photovoltaic systems are fixed. They don't alter their angle. So if you're going to design a system where the modules are fixed, what is the optimum angle that those modules get installed at? I'm going to show you how you can determine those optimum angles. What is the capacity factor of a solar photovoltaic system? And we'll see how that can be calculated as well. Okay, one of the interesting things about photovoltaics is that it has less change of cost with scale of any of the renewable technologies. If you take a large wind turbine, say a 2 megawatt wind turbine, I told you before that will cost you about $1,000 per megawatt. If you want a very small wind turbine, say a 5 kilowatt wind turbine, you'll be paying much more per unit power than that price would indicate. Whereas if you look at this graph here, which shows the typical costs over, again, a decade, 2010 to 2020, I think, yes, or something close to that. It's broken down into residential, PV systems that people put on their houses, a commercial rooftop. This might be a factory or it might be a shopping centre rooftop, up to utility scale, where the modules are fixed, and then at utility scale where there's one axis of tracking. You can see that the components of the costs are broken down here. So yellow is the module, blue is the inverter. And before going to talk more about the costs, just let me say a little bit about the significance of the module and the inverter. A photovoltaic module produces DC power. Now, that's the basic outcome of the photoelectric process. The amount of power that it produces is a function of the radiation or the irradiance, is its correct name, from the sun, and the ambient temperature. So what that means, by the way, is if you live in a place like Alberta, which has a lot of sunshine and low temperatures, then the PV resource is very good, because PV photovoltaics actually gets more efficient as the temperature decreases. So a photovoltaic module, or a string of modules as they're sometimes called, or a solar farm, will produce DC power from each of its modules. Most of the time, we want to produce AC power. And so we have to do a conversion from DC to AC. And that's the purpose of the inverter. I'll talk a lot more about inverters and their function when we look at wind power and solar power, because you need an inverter for a wind turbine as well. Although a wind turbine produces AC power, it's not the sort of power that's easily fed into the grid. So if we look at the basic costs of any of the four sizes of the systems here, you'll see that the module cost is the biggest, just about the biggest cost. And it's pretty much the same whether you put 5 PV modules on your roof or whether you have a 100 megawatt solar farm. The benefits of increasing the scale go in mainly into the auxiliary costs of the labour that you have to hire to install it and what they call the other soft costs. But apart from that, PV is pretty flat in terms of the cost per unit of power produced as a function of the size of the system. And that's one of the reasons why there's so many rooftop solar systems around the world. For example, in California, there's about 1 million rooftop PV systems in operation. In Western Australia, rooftop PV is actually the largest electricity generator on that electricity grid. And there's some very interesting issues associated with that very distributed generation of renewable and intermittent electricity. And I'll tell you a little bit about some of those issues when we get on to solar power. Okay, so I need to go to the next slide from here. Some of the features of solar power. On the top left, how the typical efficiency of a PV module has changed over the last decade. You can see there's an upward trend depending on the particular technology of the PV system. All of them have increased at roughly the same rate. But of course, that means the differences between the different technologies remain. So in 2010, we're talking roughly about 15 or 16% efficiency, and that's gone up about 2% over the last decade. Why do you think efficiency might be important for solar photovoltaic costs? Anyone got any thoughts on that? It's an interesting question, and it comes about efficiency comes in a way that you can probably appreciate if we look at this installation again. The more efficient a PV system is, the smaller the area you need to generate a fixed amount of power. So if you can increase the efficiency of a PV system, you will either get more power out of the same land area, or you can get the same power for a smaller area. And in many cases, it's an unfortunate fact of PV that solar farms are sometimes installed on productive land. So this solar farm here, or this solar installation here, is probably preventing that land from being used for any other purpose. It's not so bad, it's not so big a problem for wind turbines, because the only area that you alienate when you put up a wind farm is usually the area that's covered by the base of the tower. The area of a wind turbine is vertical. The area of a solar farm is more or less horizontal. And so that means that solar farms typically take up more area. Increasing efficiency can also lead to reduced ancillary costs, say the cost of manufacturing a complete module, because you have to encapsulate it in glass and usually put an aluminium frame around it. If the efficiency increases, the relative costs of those components go down. Here's another example of the factory prices, this time for batteries. This is the only specific battery information that I will have in this introductory slide. But what I would like you to notice is that over the same 10-year period that we've been looking at for wind and solar, the price of batteries has fallen even more. So all the major components that you need to build a renewable energy electricity system have dropped in price dramatically over the last decade. The rest of the information on this slide is really pointing to something that I'm going to spend a fair bit of time talking about in the PV section. And that is, what sort of inverter do you have with your PV system? With a wind turbine, you don't have much choice. You know, each wind turbine has a generator in the nacelle at the top of the tower. So you're more or less forced to do all your power electronics or your conversion into good quality alternating current power at each wind turbine. But with a PV system, you have a lot of choice. You can either use what's called a microinverter, and a microinverter is actually an inverter that sits on the back of each PV module. And a lot of residential systems will have a microinverter. You can have what's called a string inverter. And in the context of photovoltaics, a string means a small number of PV modules usually connected in series. So a string may contain 5 PV modules. If you have a rooftop system on your house, then that is probably a string of 5 or 10 PV modules. You can have one inverter for that string of modules. And as you would expect, having one inverter for, say, 5 modules is likely to be cheaper than having 5 microinverters, 5 modules. And that's reflected in the price here. You can also use what's called a power optimizer system. And a power optimizer typically, again, there is one per module, but the optimizer does not attempt to convert the DC to AC. It simply does a power optimization. There's a process called maximum power point tracking. I should have noted it down on this slide. Whereby the power electronics that is running the photovoltaic system or the wind turbine system, besides doing the conversion to good quality AC power, also has to ensure that the photovoltaics or the wind power are operating at the maximum possible efficiency point. And how that is done is going to be a significant component of the lecture material that I give you on those. And so a DC power optimizer doesn't do a conversion to AC, but it controls the operation of each individual module to maximize the DC production. Then you can go to a 3-phase string inverter, and that is usually reserved for the bigger systems. And you can see the bottom ones down here are all for the larger scale systems. And you can see the indicative price that you would have to pay for those. As I said, this sort of choice is particular to photovoltaics. With the wind turbine, you're more or less forced to do everything at each wind turbine. The DC to AC power ratio is just the ratio of the maximum possible DC power to the rated power of the inverter. You can usually get away with a little bit of overpowering of the inverter because for short periods they can cope with that. Right, so moving on. Oh yeah, it worked. Okay, this is probably a good place to stop. If I can get out of that, stop sharing my screen, open up another module and share my screen again. To finish off today's lecture, I will just talk a little bit about Sam. You should be able to see. Go back. New project. Okay, sorry about that. Okay. Can everybody see the software window that says on the top left, it says SAM 2020. Can you see that?
Yeah.
Yep.
Great. Okay. SAM is another project or another product of the National Renewable Energy Lab in the US. It's free, and I'm going to encourage you to download it and use it during this course. The reason I will get you to do that, apologies, is that it allows us to do some very simple, or allows us simply to do some important calculations for renewable energy projects. You can see this is the front end of SAM, and you can see you can do photovoltaics, you can do battery storage, you can do marine energy, you can do wind. So you can analyze projects that involve all the technologies that we're going to be talking about in this course. In addition, you can do a whole lot of other things as well. And I'll just give you an example of what you can do, because we're talking about photovoltaics. I've got, Ivan, I've got about 2 or 3 minutes left.
Yeah, you're good.
Okay, so let's look at photovoltaics. So under the option, or what you have here is a range of analysis techniques that you can use. LCOE stands for lifetime cost of electricity, and you can do other financial calculations as well. For the present, I'm not going to do any financial calculations. We will have a little bit of a look at this when we get into the lectures on photovoltaics, but we're primarily interested in the technical performance. So let's go to photovoltaics. And the first thing that you have to do is set the, it's kicked me out where I wanted to be, but never mind. You have to tell it where you're going to do the analysis for. SAM has a library of sites in the US that it has solar radiation data for. I've downloaded data for Calgary, and I had actually set it up for Calgary before the lecture, but for some reason it's kicked me off and it sent me to Phoenix, Arizona. So we're going to do an analysis for Arizona. So when you start the analysis with SAM, you specify the location, you move on to specify the module, and SAM has a database of a large number of different photovoltaic modules that you can analyze. It doesn't, for this very introductory purpose, it doesn't matter what it is. It's just a typical commercial PV module. You can specify the inverter as well. And again, I'm not going to talk in any detail about what inverter is the default choice in here. You then move on to system design. You can specify the number of inverters, its features, the number of modules in a string, the number of modules in an array. And then down the bottom here, you can actually input tracking and orientation. And this is one of the main things that we're going to be using SAM for, to see how the performance of a photovoltaic system changes when you change the angle of the PV installation. And that's conceptually a fairly easy computational task, particularly for a bunch of physicists, but it is messy and convoluted. The advantage of using software like SAM, and there's a number of other software suites that could be used as well, is that it does all that calculation for you and makes it very easy. That's why we're going to use it. You can also look at the way in which shading affects the performance, because anything that blocks the sunlight from reaching a photovoltaic module will reduce the power output. So you have to take that into account. Then you can look at the losses that you get within the system, and I'll talk a little bit about the typical losses when we get into that section. But the real joy of using something like SAM is you come down to the left-hand side bottom and you just press the simulate button and it does all the arithmetic for you. So what you see here is a calculation for Phoenix, Arizona, of the performance of that particular module with the inverter over a period of a year. And you can see one of the most important pieces of information that SAM tells you is the capacity factor. Okay, this is emphasizing the point that I made earlier. When we're dealing with a renewable energy system, the capacity factor is usually the most important thing you want to know. Energy yield, annual energy, they're all just ways of saying the same thing. Why do you think it's listed the capacity factor and the annual energy for year one? Anybody got any thoughts on that? It's an interesting feature of photovoltaic technology. Its performance degrades with time. Okay, over 20 years, nominal lifetime of a PV module, its efficiency will drop about 10%. And so it means that the capacity factor for year one will be higher than the capacity factor for every other year. So that's the best you're going to get out of the module. Okay, I will stop there and we will continue. We'll finish off lecture one in the class same time tomorrow. Okay, so I'll stop sharing the screen there. And does anybody have any questions or anything that they want to put into the chat? I hope this is a little bit of a calibrate. The first lecture is always a calibration exercise. Okay, you should have a sense of what the course is going to be about, and hopefully that's of interest to you. And also, too, you'll have a good idea of whether you can understand me well enough. And if you can't, please let me know so I can repeat an explanation or stop talking rapidly if I get really excited about part of the technology or whatever. But anyway, we'll deal with that. So are there any questions that people might have at the moment? Okay, if you think of any, feel free to email me, because if you email me a good question, I'll talk about it in the next lecture. Okay, I think in that case we have finished, and the same Zoom invitation tomorrow at the same time, and we will finish lecture one. Okay, thank you very much. See you tomorrow.